Now, let's talk about the mechanical equilibrium. Okay, what we mean by the mechanical equilibrium, in fact, it just means we have both the translational equilibrium and rotational equilibrium. So, translational equilibrium means that if all the forces are balanced, that means the translational equilibrium. And rotational equilibrium means all the torques are balanced. Okay. Last class we give you some example. When you have two forces, it's possible you can have all kinds of possibility. Okay, both translational equilibrium and rotational equilibrium can be broken. Okay, or both of them can be satisfied, or one of them can be satisfied, another will be violated. So, if both of the equilibrium condition, force and torque, are balanced, we call this the mechanical equilibrium. Okay, or static equilibrium. So that means there is no rotation, no translation. That's one of the things we always need to consider. For example, if you have some machine or you have some building, of course you want it in the mechanical equilibrium. So there is no tendency for rotation or translation. Okay? So the equation you need to satisfy is net torque equals to 0. Okay? And net force equals to 0. Both of them are vector equations. Okay? There are two vector equations. So if you are dealing with a three-dimensional problem, this one will have three components. This one will have three components. So together you will have 6 equations, right? So you can think about three-dimensional problem now. We have a lot of equations to deal with. The first one will be tau net x equals to 0, tau net y equals to 0, tau net z equals to 0. And you have then this one with f net x equals to 0, f net y equals to 0, f net z equals to 0. Okay. So if the force has to be balanced, the force along 3 directions should be all balanced. And the torque about z-axis, about x-axis, about y-axis, all of them should be balanced. So that's a 3-dimensional 6 equation. So that's quite complicated. We will only start with the 2-dimensional situation here. You can simplify a lot. So if you have a 2-dimensional motion like this, you have positive x here, positive y here, positive z is perpendicular to the blackboard. Okay. So if we the motion is constrained along the plane of the blackboard. So the first thing you see that you don't have to consider the force along z direction. Okay. So you only need to consider the force along x direction and y direction. So you don't have this one. Okay. And then now let's look at the torque. The torque in fact is even better. The torque is about the rotation. Rotation is along the inclined plane. Okay. So for example, if the rotation along x and y plane, so that means the torque is about z-axis. Okay, it's rotated about z-axis. So there is only one possibility. You have rotation about z-axis. You don't have rotation about x-axis. You don't have rotation about y-axis. Okay. So for 2-dimensional motion, you have only one kind of rotation. So you don't have this. You don't have this. You can compute 2 rotational equations. So for 2 dimension, you have 3 equations, not 4. Okay? For the torque balance. So that means if the motion is on the plane, two-dimensional motion, if you want to make the mechanical equilibrium, there are three equations to satisfy. One torque equation and two force equation. Okay? Any question here? So we have three equations here.